Our next speaker is Doug Downey, who is an associate professor at Northwestern University and a research scientist at AI2 on the Semantic Scholar team, working on knowledge extraction from large corpora. He's won numerous awards for his work, including a Best Paper Award from IJCAI, an NSF Career Award, and a Microsoft New Faculty Fellowship. Hey, Doug.
Okay, can you hear me?
Yes, we can hear you.
Great. I also wanted to enable video. Sorry for the delay.
No problem.
There we go. Okay, thank you. So I am delighted to be here speaking with you today. Let me Delighted to be here speaking with you today. I'm going to talk about mining the citation graph for representation learning and concept extraction. So to motivate this work, I'll tell a story that many of you are probably familiar with. So information overload is a problem in science. There are millions of papers published every year in tens of thousands of journals, and the pace of publication is increasing every year by about 5%. And because our ability to read papers is not necessarily increasing by 5% every year, we're spending a large amount of time navigating the scientific literature, trying to figure out what we should read, and then trying to process it efficiently. And a lot of this publication is overwhelming for human scholars. So in response to this problem, the Allen Institute for AI launched a scholarly search engine called Semantic Scholar that's aimed at helping scholars find the information they need more rapidly and then consume those scientific papers, the key insights and the results, more quickly. It's not the only scholarly search engine, and there's still a lot of work to do to fulfill its promise, but I'm excited to talk to you today about a couple of areas of progress. So the research I'm going to discuss today kind of turns this information overload problem on its head a bit, and it uses this insight that information overload is bad for human scholars, but it turns out it's kind of just good news for algorithms. So more papers is just more data that methods that learn from unsupervised approaches, learn from unlabeled data, can exploit to perform tasks. So I'm going to talk about two methods that use this strategy. In particular, they use this citation graph from unlabeled papers to perform two tasks. One is learning paper embeddings, and the other is extracting concepts from scientific papers. So I'll discuss each of these in turn. So let's just jump right in to talk about paper embeddings. So in this task, you're given a scientific paper, and the goal is to learn a vector representation of that paper, also known as an embedding, such that similar papers tend to get similar vectors. And machine learning techniques rely critically on these vectors, and if we had accurate vector representations, we could use those to power applications like recommendation and search and classification and so on. So a natural approach to this task would be to use a pre-trained transformer. So this bar chart shows the ceaseless progress of variants of pre-trained transformers on this GLUE benchmark, which is a benchmark of NLP tasks. So it turns out that this approach doesn't work super well for our task. So this GLUE benchmark is a sentence level task, and pre-trained transformers work great there. But they work less well on tasks that involve representing full documents. So there is still some work to do. So why is that? Well, these pre-trained transformers are trained on short token level contexts of a few hundred words. And this has been a great strategy for building models that can process sentences, but is less good if we want to represent documents. And in particular, these pre-trained transformers that use a variant of the language modeling objective tend not to use any corpus level signals, like which papers cite which other papers, which happens to be really helpful for representing documents. So the method we introduced is called SPECTER, which stands for Scientific Paper Embeddings using Citation-Informed Transformers. And it's going to use both the power of these pre-trained transformers at representing text and corpus level context in the form of the citation graph. So stated simply, we're going to use the intuition that if A cites B, A is more similar to B, and we're going to fine tune a transformer on that signal, and it's going to result in paper embeddings that are better than if we didn't. Okay, so to describe the method, it's actually quite simple, and it can be described quickly. So a baseline approach that would use a pre-trained transformer off the shelf that would take in a query paper and an amount of text from that paper that we could plausibly hand off to a transformer, and the title and abstract is kind of about right for most off-the-shelf transformers. And we could just submit this text to one of these pre-trained transformers and get out a vector representation and call that our paper embedding. This turns out to not really work at all, right? So in fact, it's an extraordinarily poor strategy. I'll show you the numbers in a minute. So you can't use this off-the-shelf approach. And what SPECTER does instead is it's going to fine-tune this transformer on an objective that comes from citations. In particular, we'll hand this transformer a triple of papers. So a query paper, a paper that query is related to because it cites that paper. So query paper is Q, the related paper is P+, which is cited by paper PQ. And then we'll also give it an unrelated paper, P-, that is not related because Q does not cite it. And then we'll fine tune this transformer to pull the representations of the query and the cited paper close together and push the representations of the query and the uncited paper farther apart. So specifically, D in this loss function stands for distance, and we want the distance between the query and the positive paper to be small relative to the distance between the query and the negative paper, and we want that gap to be at least as large as M, which is this margin parameter, margin hyperparameter that controls the objective. And that's essentially the whole method. There's one nuance in how we choose the negative examples. So the positive papers, P+, are always those randomly drawn from papers that the query cites. However, those negative examples, P-, are generated in two different ways. So we have easy ones, and those are just randomly drawn papers from the rest of the corpus. Sometimes those are kind of too easy and don't provide enough of a training signal. So we also mix in what we call hard negatives, which are papers that are not cited by the query, but are cited by a paper that the query cites. And it turns out training on a mixture of these is helpful for performance. Okay, so that's the whole method. So we did an experiment training this model on about 700,000 triplets. As the base pre-trained transformer, we used a version of BERT that was fine-tuned on, or it was tuned on scientific text called SciBERT. And so how well does it work? This turns out to be a little bit of a tricky question because there isn't a standard data set for evaluating academic paper representations. So we built our own thing. The intuition behind this was that we want our embeddings to perform well across many tasks. And in fact, we want these embeddings to be things we could just share for a paper. So given a paper, we could share a 768 dimensional vector of that paper, and people could use it without having to fine tune their own SciBERT model themselves. So with those as like guiding principles, we built this data set, SciDocs, that's a benchmark across several document level tasks. A few try to predict user activity from user activity that we mined from Semantic Scholar. So trying to predict which papers people will view in a session or in a list of recommended papers. And then also a classification and citation prediction task. So here are the results. There's kind of a wall of numbers here. I won't belabor the details, but we evaluated against several methods from the recent state of the art in representing long texts. And we found that SPECTER outperformed these previous methods in almost every case and also on average. A couple of things that I'll highlight This row third from the bottom is that baseline approach that just hands the title and abstract off to a pre-trained transformer. And you can see it's, aside from the random baseline, it's the lowest scoring approach in our experiment. So it really doesn't work well. The other thing I'll mention is that the gap between SPECTER's performance and the next highest baseline gets decreased by about half if you remove those hard negatives. So that that more challenging training signal turned out to be pretty important in providing a margin of victory over the previous techniques. So SPECTER is being used in a handful of applications. So we have an adaptive feed tool on Semantic Scholar. In the interest of time, I won't demo this, but I encourage you to try it. So it's this button called Research Feeds at the top of the Semantic Scholar page. I use this at least every week to help me stay up to date with recent research. It provides recommendations using these SPECTER embeddings. A couple of search tools built over the Cord19 data set are using SPECTER embeddings to help power certain aspects of those search tools. So the Cord19 data set is a set of papers about COVID-19. And also SPECTER embeddings were one ingredient that helped power winning results in this Trek COVID competition, information retrieval competition. Here's a tweet where Sean McCavney is talking about his winning system that used SPECTER embeddings. Okay, so that's the short story on SPECTER. It's an embedding method for scientific papers. Importantly, it only requires title and abstract, so we're not actually using the citation graph. We don't need papers to be cited in order to produce embeddings with SPECTER. So you can use this on brand new papers. Please check out the code and data set if you get a chance. Okay, so now I want to switch gears to the second use of the citation graph. This is another simple algorithm that resulted in some pretty strong performance. The task here is concept extraction. So the input is a corpus of scientific papers, and we want to output the key scientific concepts. And this task's a little tricky, so we'd like to know that things like ELMO, gradient penalty, and asynchronous advantage actor-critic are key scientific concepts that you could imagine, say, a Wikipedia page being written about and describing those concepts. Whereas other terms that are common in scientific literature, like popular conjecture or input graph, are not specific concepts that you can describe on a page, but instead are sort of common noun phrases that are often used in a variety of scientific contexts. So this is our task, is to automatically mine these terms on the left and distinguish them from the terms on the right. If we could do this, we could do a bunch of exciting things like faceted search and trend analysis. And this is the first step toward building a high quality scientific knowledge base that's also comprehensive. Okay, so the algorithm we built for performing this task is called ForeCite. And it uses the citation graph to perform concept extraction. It uses a simple intuition that when scientific concepts occur in papers, they're typically introduced or popularized by one paper, and other papers that mention the concept tend to cite that one paper. This is not always true, but it's sort of true often enough that if you use it as an intuition for a concept extraction method, it works quite well. So others have used the citation graph to mine concepts before, so I'll spend a minute talking about the distinction between ForeCite and these previous approaches. So here are two what are called phrase subgraphs. So these are nodes here represent papers, edges represent citations. And imagine we're isolating a part of the citation graph that includes all papers that mention a particular term. And there are two different phrase subgraphs here on the left and on the right. These two phrase subgraphs have the same number of internal edges. And previous approaches that would use the phrase subgraphs would actually treat these two graphs as the same in terms of what they indicate about which phrase is a bona fide scientific concept. All else being equal, having a phrase subgraph with more internal edges is a positive signal that that phrase subgraph actually corresponds to a real scientific concept and not one of these general terms like input graph. However, ForeCite uses a different intuition. So ForeCite's going to identify that this right-hand graph has one node with a much higher integrity than the left-hand graph does. So in the right-hand graph, we have one node with an integrity of 4, whereas the max integrity of the left graph is only 2. And ForeCite's going to say this graph on the right is much more likely to represent a real concept than the graph on the left, whereas previous work would have treated these two graphs as equivalent because they have the same internal density. Okay, so that's the key distinction of the ForeCite intuition. Here's the math, which I guess I can briefly describe. So ForeCite is going to return a score for a citation subgraph. So the subgraph of all papers that mention the term T. And it's going to increase with the fraction of papers that contain the term and cite. So, sorry, the score is a maximum over the papers, the nodes in the subgraph. And a paper gets a score that's equal to the fraction of papers that cite that paper and include the term, divided by all papers that contain the term, and then multiplied by this log term that just rewards papers that are more cited by papers that include the term. So this is just the mathematical statement of the intuition that I described on the previous slide. And it's going by a little bit quickly, but hopefully that's enough to give you the flavor. Okay, so here's why I'm telling you about this today is that this approach actually works remarkably well. So when you find terms that have papers that score high, according to the score on the previous slide, so really look like introducing papers that get cited by a lot of papers that use the term, overwhelmingly those terms tend to be really high precision scientific concepts. So this precision recall curve on the left, you can see that the ForeCite method, which is the blue line, has much higher yield at high precision than these other competing methods from previous work, SciNLP and LOR. And we see a similar kind of trend when we evaluate precision at K on the right-hand side. So ForeCite scores much higher at each of these K, and in particular at the really high precision end where K is 100 or 1,000. These concepts were manually annotated, and the task actually has some subjectivity in it. So there's a little bit of fine print in these results, and I encourage you to look at the paper and also the annotator instructions, and let us know what you think about that if you have thoughts. So there's a little bit of subtlety there, but but we do think ForeCite actually performs quite well at the high precision end. Here's an illustration of some real citation graphs for a couple of terms. So on the left we have BERT, and the blue edges here are citations to the introducing paper. And the orange ones are citations to other papers that contain the phrase, but not the introducing paper. So you can see BERT on the left looks very different from unseen class on the right. And we would call BERT a good concept and unseen class not a good concept. And the BERT graph just has a whole bunch more blue relative to orange. Lots more links to the introducing paper than to other papers in the term subgraph. Here are the top 5 concepts for each of these 3 different methods. And one of the things this shows is that qualitatively, ForeCite tends to return much more specific concepts. So these tend to be specific systems or techniques rather than ideas like adversarial examples that can be used in a whole bunch of different techniques. Those other things are more commonly returned by these other methods. All of these are fairly high quality, so there's only one that we would call a mistake here, and that's received signal. In another limited experiment, we measured how often each of these concepts occurs in Wikipedia, and ForeCite tends to identify more emerging ones, although this is a limited experiment, but we found that 30% of ForeCite's top 20 occurred in Wikipedia versus 90% for lore.
A couple minutes, Doug.
Great, thanks. Yeah, so just to wrap up, let me give you a hint at kind of where we're going with this. So we have a reasonable solution to this very first problem, which is identifying the scientific concepts. We want to move beyond that to generate definitions of these concepts that could go on a topic page, kind of like a Wikipedia page, but for the long tail of science, which is kind of very underrepresented on current Wikipedia. And because these definitions won't be perfect, we'd then like to reach out to authors who have written about these ideas and enlist them to improve those topic pages so we can create a nice scientific resource that describes all of these long tail scientific concepts. So just briefly, I'll show you a very preliminary results on this, and this is late breaking as of last week is when these results were created. This is a summarization approach that has an extraction step and then uses an abstractive summarizer. It's trained on Wikipedia. And here are a couple of descriptions of a couple key scientific concepts produced by that system. So I'll give you 20 seconds to read through these just to give you a feel for what that output looks like today. And you can see there are certainly some mistakes here or some less important text. And attribution is going to be really important, so saying where this text came from. Okay, so then that's ForeCite. So it uses the intuition that concepts tend to be introduced by a single paper, gets really high precision at for certain sets of concepts. And our next step is to do a semi-automatic authoring of topic pages and try to create topic pages for the long tail of science. Feel free to check out the code. I'd like to thank these contributors who did the vast majority of the work I'm describing today. Thank you very much.
Thanks so much, Doug, for the great talk. I think we have time for maybe like 2 questions, one per paper you presented. Amardeep asks about regarding SPECTER. Why does the pre-trained transformer perform poor? Just given the abstract title and conclusion on information dense.
Yeah, I mean, I think, people have seen maybe similar things in other tasks where when you don't fine tune a transformer for a task, it doesn't always do great. But I think the story is really that document level semantics is kind of a different endpoint than this within document mass language modeling objective that the pre-trained transformer was trained on. So it's not aimed at producing a single embedding that captures the semantics of the whole passage, at least not in the sense that we were consuming it in the paper embeddings tasks. So I don't have a great reason for why that's true, and I would say I was a little surprised by how bad it was. So I'm still a little bit, I think, puzzled by that result, but I think it's really the difference in a sort of document level topic objective versus the token level mass language modeling objective that drives a lot of it.
Awesome. And then Yoav asks, the scientific concepts extraction algorithm is very cool. How domain independent do you think the heuristic is? Will it work on biochem, physics, as well as CS?
That is a great question. I would think or hope it would be fairly domain independent just because it's so simple and it just uses the citation structure. I don't know, is Daniel King on the call? Do we have results on bio that have been labeled at all?
Can you hear me?
Yes.
Okay. Yeah, not like, so we did a little bit with a PubMed corpus and I ran it on the Core 19 corpus. And there's certainly some differences in the citation structure, like, CS has this tendency to name stuff that's not necessarily present in every field, or at least current CS. But the top concepts looked to be similar precision in bio, which is the other domain that I've run it on. I haven't tried other domains.
Great, thank you.
Definitely there's citation pattern differences across fields.